let's go ahead and get started. So where we left off on Monday was this midterm grade calculation example, just any sort of array processing example, meaning meant as an illustration of kind of the relationship between the data we have in our program that may make sense to store in array form, and then a looping structure that would iterate over that array to do some reading or updating or analysis of that data. And looking at some of the demos for the coding practice that was due today, where it was just loops without necessarily arrays, I think some of you kind of saw that. It's actually a little hard to come up with examples of using loops that don't have arrays associated with them. But now once we have an array, having a loop that processes that array, I think is just a very natural fit. This was the code we came up with on Monday, and it worked generally pretty well. I just wanted to check your understanding of this code. So we kind of typed this up together, and I just want to make sure everyone's on the same page here. Why did we pound define max students 50? Why did we have that in the code? It'll be a common thing we'll have, but why? Why for this example did we do it? For a couple reasons, that's definitely part of the reasons, right? So we talked about this idea of having to allocate our arrays. If it's a single variable, a single int, a single float, we don't really have to think about memory allocation at all. But now when we have these arrays where by declaring a single variable name, we have the square brackets, the size, the amount of space that array takes up is something we have to think about as we're writing our program. There's advantages and disadvantages to the different approaches, but one such approach we refer to as static memory allocation, where at compile time we know the length of that array. And that's what this example is doing here. This code works for an example in which you have 50 students or fewer. It would not work for 51 without having to change it. The reason we're doing this pound define, and it's a very common design pattern in C, is that it still allows us to have a statically allocated array, but if we write our code accordingly, both the allocation for that array, how many integers are in that array, as well as being aware of the length of that array when we're doing the coding for it, using this versus hard coding something otherwise, then in theory, if we decide we want to change the problem to allow a maximum of 51 or 500 or really any reasonable number of maximum students, it's kind of a one-line change, right? If we've written the rest of the code correctly, we change that little pound define, and the rest of the code just kind of follows. This problem is scoped so that it can be solved via static memory allocation, because it says there are 50 or fewer students. So if we allocate 50, we're good to go. If it turns out there was only 3, like one of the instances where we ran with only 3, then it still is going to work here. So that's one element we had here. It's a pretty common design pattern that if you have some constants in your program, not just to write the constant as you need it, score was 60. That was just also given as part of the spec for this problem, that the maximum score on the test was out of 60 points. We could have just written 60 elsewhere in our program, but if we do that max score pound define, it doesn't need to be in all caps, that's just kind of a habit I've fallen into. But you have this pound define, it's a pre-processor macro for the compiler. Literally, every time this max score token is seen in the rest of your program, the compiler's going to replace it with what comes after the pound define. And again, that just gives you a little bit of that flexibility without having to worry about every time you run this program, please enter in the maximum number of students, or please enter in the maximum score. You can still change it, you just have to recompile when you change this. We had a loop, had a local score variable. We talked a little bit about the scoping rules, that current score is only a valid variable within this loop because of where it's defined. We could have defined it up here and it still would have worked, but this kind of gives that hint that this current score is only relevant for this loop in which we've created it. We enter in the score with our printf, scanf kind of prompt here. Why do we have this code here? If cur score equals -1, break. Why are we doing that? Sure.
Because it says like if when you want to stop, the user is going to input -1, and then if it breaks, then we go out of the loop. Otherwise, it will continue till 50.
Right, and so as you were coming up with your own solutions for this on Monday, some were doing a do-while loop, others were doing a while loop. And those were also completely valid as well. We could have had a do-while loop that would check while current score is not equal to -1, and you could have written such a program that would have made sense. For this structure in which we have this array of length max students, at least for me, and again, one isn't better than the other, but at least for me, this was kind of the natural connection to make. We have an array of length maximum students, kind of just naturally leads to a for loop that does I equals 0, I less than max students, I plus plus. We just need a way of getting out of that loop before we potentially reach that number of max students, and that's what that break keyword is going to be used for. We've seen break keyword in our switch statements, and it kind of does the same thing, although we think of it as more of a I'm done with the switch statement. It's the same thing, it's I'm done with my for loop. And I'm done with my for loop when I received a score that was equal to -1. That was just part of the problem spec. If someone types in -1, you're done. There's no other grades or other scores to analyze here. We talked about how, this was an if, the rest of this body could have been an else underneath that if, but it actually doesn't need to be. It would have still worked with an else statement there, but it really doesn't need to because the control flow just kind of breaks at that point. If the score is equal to that break, we are done with the loop entirely. Otherwise, keep doing the rest of the things we have to do in the loop. In this case, update the value in our array and keep track of, for purposes of averaging, how many valid scores, that's called count here, how many valid scores we currently received. So this is a pretty common design pattern where you have some value that's being entered, you do some initial analysis on it, you determine if you want to keep going in the loop, and you update an array accordingly. And that allowed for that code then having that little bit of complexity. The code that actually does the averaging was pretty straightforward. We just added them all up, divide by the total count at the end. Sure.
If there's like another if loop nested in that and the breaks inside the second one, does it end both loops or just
So it breaks out of the innermost loop only. And that code, if you really wanted to get out of the entire nested loop, going to look really ugly. So, and you can do it, right? You would have an if condition in the inner loop that breaks out of the inner loop, and then as soon as you go to the outer loop, you have to have a kind of similar looking if condition that breaks out of the outer loop. That's usually a sign that something's a little, messed up with your looping approach, that you're having all sorts of break statements all over the place. But this kind of approach is pretty common. There's maximum number of things I'm going to process. It may be fewer than that. One way to check if it's fewer than that is to have a while loop. Another way to check is to have a for loop and just break out of that for loop early. So have that in your toolbox and understand that this approach of allocating potentially more things than you need, it's technically kind of memory inefficient. I've allocated 50 students and I only actually needed 3. I only needed space for 3. Well, at this scale, that's probably okay. And it makes the rest of the code relatively straightforward to write. You write it assuming max students. You then break out early if you recognize there's fewer than the maximum number of students. And then the rest of the processing is a relatively clean thing to have in place there. That's our single dimensional arrays. And in C, we are allowed to have then multi-dimensional arrays by contrast here. So the type of arrays we work with are technically single dimensional or one-dimensional arrays. The other term they would just be referred to as a vector. Vector refers to the mathematical construct. Array is the programming construct, but it's kind of representing the same thing. A single dimension of data representing something. So we have this syntax, I think, nailed down. If we initialize it, we don't actually have to declare the size of it, but we can also declare the size of it. Int A1, the size of it's what's in those square brackets when we declare the variable array here, and it's going to allocate 4 of those integers. It's going to allocate 16 bytes in memory where we store those values represented here. We can have multi-dimensional arrays as well. The second most common one would be just a 2-dimensional array. The mathematical equivalent would be just referred to as a matrix, where you have not just a single kind of growing array of values, a single vector of values, you have multiple dimensions to it. And the syntax is just something you have to get a little bit of experience with as you have multiple dimensions, where you declare each of the size of the dimensions in turn. And then you can actually also allocate or initialize all those values here. You allocate it essentially row by row, and that's what that's attempting to visualize here. So the entire thing is being initialized. That's that first curly brace. Of that entire thing called A2 we're initializing, the first 4 values correspond to that first row, second 4 values, the third 4 values, and finally the last 4 values correspond to that final row that we have there. The kind of nice alignment of the data is just to make it look nice. You don't have to have the new lines or anything like that there. But you should think of it in terms of that row by row format here. You can have more than 2 dimensions. There's probably some upper limit, but for practical perspective, there really isn't. But it's pretty uncommon in your code to have something like this, where you have a 4-dimensional array of data that you're trying to keep track of. It's just a function of the type of things we do with the programs that we write. We've already kind of seen this, right? If we're going to process an image, a 2-dimensional array makes a lot of sense because we have just the pixels at those locations, and you can think of it as being a 2-dimensional array and access it that way. We can think of all sorts of data that require 3 dimensions, anything that's kind of a volume in 3-dimensional space that we want to manipulate. Maybe 4 dimensions if there's some time element to as well. Anything bigger than that is less likely to be a common thing you would have. And if your program, if you think it needs 7 dimensions of an array, it's probably a sign that you could probably decompose the problem a little bit different than what you are currently doing. But C does let you do that. You can have, within reason, almost as many dimensions as you would want. Other languages do this differently, but in C we do that subscripting of the array from left to right. So we've declared this 2-dimensional array A of size 4 by 4. First dimension, you can think of that as the number of rows, is 4. The second dimension, you can think of that as the number of columns. That is also 4 here. So when we access A of 3, 2, we first access that first dimension, and then we access with 3, then we access the second dimension with that value of 2. So A of 3, 2, however you want to say that out loud, is 0, 1, 2, 3, the third row, or the third offset row, or the fourth row here that we have here. In the first dimension, 0, 1, 2, in that next dimension, that's why that value would correspond to 15 here. It is exactly the same here, but you just now you're keeping track of a couple dimensions, right? Where if it was our single dimension case, A of 3 would be 0, 1, 2, 3, so it's either the third offset from 0 or it's the fourth element in our array. It's the same exact thing here in both of our dimensions. A is of size 4 by 4. When I access A of 3, 2, that's 0, 1, 2, 3 in the first dimension, 0, 1, 2 in the second dimension. It's pretty hard to draw it once you get to 3 and 4 dimensions. Eventually it's impossible to draw it, but in 2 dimensions we can still draw it out. 0, 1, 2, 3, 0, 1, 2. That's why A of 3, 2 is 15. Following along with that, what is A of 1, 0 for this example? It is 5. If you don't have that now, that's okay. Come back to this after you're reviewing slides, lecture video later. It is going to be 5. Offset 0, 1 in the first dimension. Offset just 0 in the second dimension. What is 1, 2? Awesome. 3, 0. 0, 3. 4. I think it's a nice thing. If you get it backwards, you just get it backwards. And that's something, okay, I did IJ and I should have done JI in my code, right? It's one of those 50-50 things in terms of getting it right or not. But in this case, it is row first, then it is column. What if I did 4, 1 in my code? So 4, 1 is a problem because it's outside of our range of our array. Okay, not meant to be a trick question, but it's true. It's bad. Replit may return 0 because it's outside your, who knows? There's no guarantee it's going to return anything specifically, because as we do the math there, that 0, 1, 2, 3, 4, and then 0, 1, it's whatever's going to be in effectively location 18 in memory here, but we don't have that. We haven't allocated anything there. Replit for you may 0 initialize for you. It may give you a seg fault. It may cause all sorts of problems. That would be a bug in your program if you accessed for an array of size 4 by 4, if you access something of A, 4, 1. It's just like our array of size n in just the single dimension. If we actually access A of n, that's also a bug, right? Because it's 0 to n minus 1 are the valid indices. The same exact thing here in the multi-dimensional case. If it's of size n by m, then our valid indices are 0 to n minus 1 to 0 to m minus 1. And I don't know what to tell you other than that's just something you really got to just remember when doing C programming. And when in doubt, print it out, right? That wasn't meant to rhyme. But when in doubt, confirm that the data you're getting is what you think you are having, and you'll trace down and figure out those bugs early versus writing all of the code and trying to figure out why it's not getting you the final result that you are expecting. How this multidimensional layout of data works in practice is an implementation detail that C as a standard does specify. The term you could look for is called row major order. It is sometimes relevant to us in terms of how things get laid out in memory, but I think for the programs we're writing this semester, you're not going to have to play around with that because we have this 2-dimensional data structure, But ultimately, memory is this one-dimensional kind of thing, or at least the programmer's view of memory is a one-dimensional kind of thing. So this two-dimensional thing effectively does ultimately have to get linearized. That's true if it's 2 dimensions or if it's 15 dimensions. It ultimately has to kind of get mapped to a linear address space in our memory. And there is an equivalency one can typically do where you kind of just take your column offset and then add that to our X offset that we would have here for each row. But we probably don't have to play around with that too much this semester. As always, as part of our problem-solving process, it's more about, what variables do I need? What data do I have to represent? And now you have to add, is there some dimensionality to the data? Does it need to be just a single int? Is it a single dimensional array of ints? Is it now going to potentially be a 2-dimensional array of ints? Our for loops still kind of work. And in C, unlike other programming languages, this array type is not sort of a first-class citizen of the language itself. So the kind of things we are getting accustomed to doing with individual scalar kind of non-array variables do not work when working with entire arrays. So if I have an array A and an array B, I cannot just say B equals A or A equals B. I can't just compare the equality between 2 arrays. I can't assign one array to another array. At least I can't do it with one line of C code. Once you have arrays in your programs, and I already saw a couple of examples with like sort of the coding practices even from this week, but once you have arrays in your programs, you have to be thinking in terms of the loops to process them. Either loops or existing functions to process them. Don't assume, unlike in other programming languages, like MATLAB is a pretty good example of that, that you can just do the kind of things you were already doing with the operators, with assignment, with relational operators, arithmetic things. You cannot do that with arrays themselves. You'll have to have for loops that then do that for the individual element by element basis for those arrays. I think that's important enough that I want us to go through an example of just, for example, copying one array to another array. You can't explicitly just copy it directly. I can't say in this case, if I have some value A and some value B, I can't set A equals B. I can't check A equals B. Technically it's valid syntax, but it would actually just be checking the addresses of A and the address of B. Usually not what you would want. Instead, if you really want to check if array A is equal to array B, you'd have to check it on an element by element basis. If I want to copy array A to copy to array B, you have to do it on an element by element basis. There are also then functions that do that for you. This is missing a closing brace for whatever reason, because I have opening braces here. But otherwise, this is the kind of design pattern you're going to see in your programs when working with arrays over and over again. If it's a single dimensional array or sort of vector type, you'll have a single for loop most commonly. If it's going to be a 2-dimensional array, you're very commonly going to have a double nested for loop associated with it. And with an n-dimensional array where n hopefully doesn't ever get bigger than 3 for the programs you're writing, you're going to have that many nested for loops to access each individual element within that array. And we just want to keep track of which one is corresponding to which one. And it's the kind of thing that will just take a little bit of practice and a little bit of muscle memory of, okay, I have this array. How do I now do stuff with that array? Let's get some practice doing that together. I'll drive it here, but help me out with some suggestions as we go for this exact array copy example here. So this is in Replit under, I think it's just called array copy in a Replit for lecture 5 here. And we're doing something kind of similar with our static memory allocation as what we were doing previously with the midterm scores example, where now we maybe have 2 things that we're defining because it's a 2-dimensional array. Could be called max x, max y, but here we're calling it the number of rows and the number of columns. And that allows us to still statically allocate those arrays. And now we're statically allocating both dimensions of a 2-dimensional array here. So we declare our int a of size num rows by num columns, int b of num rows by num columns. And now if we want to initialize a to some random value. So let's say initialization of array A for values in range -10 to 10 or something like that. The design pattern is very similar. So for our single array, we have that single for loop. And you can create your own variables, but this local int variable I that does the rows. is going to be a very common way of doing it. Likewise then, now that it's two-dimensional, we'll have this inner loop, which is going to be doing the j's. And now, for whatever we're going to do within here, it's going to be a of I is just one way to make sure that this code that's initializing a is going through and doing every single element of A00, then 01, then 02. This is doing it on a row-by-row basis. It turns out from a performance perspective that is generally the right way to do it in C, but if we did J then I, it also would have been just fine for this example. If we did the J loop followed by the I loop here. If I want to initialize A of I sub j to, let's say, for random values in the range -10 to 10, let's talk about this, because this has been coming up in all of our different lab examples here. We have this rand function defined in standard lib. Rand returns a random integer, I believe in the range 0 to like integer max is what it returns. We have this operator that allows us to kind of limit the range of what gets returned by that by taking the remainder, right? By taking the modulus of that operator and saying, mod 100 or something like that. That, by doing the mod operator, we're dividing by 100 and returning the remainder when dividing by 100. That's going to take our relatively random value and return instead that large random value, but now kind of shrunk down to a range of 0 to 99. When we divide by 100, that's either perfectly evenly divisible, in which case the remainder is 0, or the remainder is anything between 1 and 99. If we wanted to have our rand function return values in the range -10 to 10 now, well, how would we do that? Mod 20 is promising. That returns a value in the range 0 to 19. So how do we get it in the range -10 to 10? It's close. So again, if you just think of it in terms of those terms step by step, you'll figure out the answer to this one quicker than I think otherwise you would, right? Mod 20 returns something in the range 0 to 19. If I subtract 10 from that, I get something in the range -10 to 9, right? So how would I get it to do something -10 to 10? Mod 21, right? That gives me something in the range. And that thought process is what I want you to think about. And I don't do that to be mean, but I do want you to think about like the arithmetic that's happening here. Okay, mod 21 gives us a value 0 to 20. I subtract 10 from that. That does give me a value -10 to 10. That's technically 21 different values, right? Because you think about 0 and then the -10 and then the +10. That's 21 different values. So mod 21 kind of makes sense if you think about it in those terms. I would then say, okay, we've initialized A. Let's just print out A. Someone had provided a good example of this. Printing out multidimensional data is kind of ugly too in C, or at least we have to think about it in C, unlike other programming languages where we just do a print statement of that. It's going to be very similar in terms of like this structure, where we're going to eventually have to print out every single value in here, but if we want to make it look good, we have to think about that a little bit. We know we're printing out A of I of j ultimately here. If we actually were to run this, it doesn't really look especially, two-dimensional here, right? Because it's just printing all, 50 values one after the other. I mean, it's correct because it is the 50 values of A that we've generated. They do appear to be in the range -10 to 10, so the random is working pretty well. But if we want to print it out nicely, we have to kind of think about the for loops, how the inner loop kind of interacts with the outer loop if we want it to look nice. So we'll say A of %d equals, where %d in this case would be like the actual number of rows and number of column. So if we want to print it out on a row by row basis, let's do, hey, this is the first row. And then if we want to make sure we're printing out the last element special, then we want to make sure we actually only going to print out num columns -1. And then for the last one, we can do something like, that's the end of the row. And that's a kind of design pattern that will kind of, as you do it over and over again, will kind of make sense here. We're missing something here. %d, and we actually print out the last value of A of I of num cols -1. So now we're saying instead of just doing everything within that inner loop, we're peeling what the last iteration off that inner loop and printing that one separately. And that's what's happening here, right? Do everything but the last element of the array in this kind of steady state %d comma space. But then for the last one, I guess that's the last entry here. I think it probably makes sense to do, I had that, but I deleted it. And the actual bracket representing that entire row, and then add a new line at the very end, and then adding a new line at the end there. That looks meh. Let's see if we can make it look a little bit better. A of this equals that. We could add a new line at the end, and a new line here. That would at least keep things kind of aligned a little bit better. And let's try that. I don't think it looks wonderful. Technically, that last one has one extra comma. We'll leave it at that for now. I mean, we could remove that last comma using the same thing where we check num rows at the very end slightly differently. But for now, that's probably good enough. Okay, we're printing out 5 by 10, so 5 rows, 10 columns here. And now the idea is we have to copy this A into this other thing called B here. And now that, I would even recommend, hey, copy pasting kind of this structure. I need to do something to every element of A and grab an element of B. So we know it's going to look something like that, right? For every row, for every column, do something with A of J. If I want to copy every element of A into every corresponding place in B, how do I have to modify this line 34 here? Okay. Equals A of J, and that should do the copy. If we wanted to confirm that this code is working, what else should we add to it? Oh, there's even a little comment. See, that's unfair. We should probably print out B as well. If I want to print out B, for me at least personally, I have all this code, I put some effort into it, I'm just going to copy paste it. That is printing out A, so you have to be a little bit careful. A good editor would be smart and would let you do a replace of a selected area. Every time I see A, gotta be a little bit careful. Let's match case. Every time I see A, I want to replace it with B, and that's a little, worrisome. But it should only be for a certain selected area here. The likelihood of me screwing that up is too high. We'll just do it manually, but you have to kind of look at line by line and making sure you do it. Okay, I'm printing out B. I'm actually wanting to make sure I'm printing out B. So every time I have that A reference, I'm going to just replace it with a B. And this should work. So, I don't know, let's add a couple new lines before we print out B here. A of 510 is this, B of 510 are the same exact values. And it works pretty well, for that purpose. Now, there is another way to do this. So, I mentioned how these arrays in C aren't kind of first-class citizens, right? We have to kind of operate them on an element-by-element basis. But there are a lot of standard library functions that allow us to do the kind of things you typically would write via several sets of for loops via single function calls. And I think the tricky part about learning C programming, certainly the first time you get this experience, is there's almost always a function that does what you need to do when you're working with arrays, or as we see on Friday, working with strings. Now, the tricky part is to figure out what the name of this function is. There is a list of all of them, but it's kind of hard to look through this huge list and know this is the exact function that does exactly what I want. And I don't think that's a straightforward thing. I think part of my role is to help kind of guide you and nudge you into a particular direction. And on a lab assignment, I'll say, you should really take a look at this function. This function might be really helpful. Well, let's do that for this example. It turns out this kind of operation of copying blocks of memory is so common. There's a function that's defined as part of the standard C library that does that relatively efficiently for you. And it's called memcopy. The syntax for it, like all of these functions, is a little painful to understand at first blush. And the next, to have this open is one thing. The next thing you want to look to is some examples of it in usage. But even those examples are kind of painfully written to be as clever as possible sometimes. But we can look at it and try to kind of figure out what it's doing here just based on the technical documentation provided here. This is always a good thing to ask. Okay, I've told you need to use memcopy. I gave you the link to it. You know, what is the exact syntax for it is something that I'll point you back to that documentation. I'll say, you know, read it as literally as possible, but then let me help you when you get stuck. It's dealing with the pointer syntax, which I talk about how there is a direct relationship here, but for now, the only thing you have to know is when something calls for a pointer, you can provide it the name of the array, and that is a pointer to the first element in that array. So the syntax is void star. Memcopy is the name of the function. The first input is the destination of what I want to copy into. The second input is the source, the thing I want to copy from. Why is it destination first and source second? It just is. I don't know what to tell you. But that's it. So it's destination first, then it's source second. And then the final thing, the final kind of gotcha is the last thing it's returning is the number of bytes that I want to copy. So that's destination, source, and count, which I guess if they'd called it byte count, that would have been a little bit easier. But we should be able to work with this. So that's the declaration for it in the documentation. I want to call memcopy. I'm copying A to B, so which one is going to be my destination? Is it A or B? It's B. Copying to A, and if you get this part, you are in very good shape, because I don't think it's obvious. The last thing is count. It's the number of bytes I need to copy. How many bytes do I need to copy? It's something we can write the program for. I mean, we have to be able to do this, but how would I figure out how many bytes this is? That's very promising. Let's start with that. Number of rows times, okay, it is, right? 5 by 10, that's 50 things we've allocated. That is not quite right, you know, but I commented out the wrong thing here. I wanted to comment out the copy code and keep the print code. So let me just fix that while we run this here. So I still want to print out the result of B. I just bulk copied commented out the wrong thing. This is my replacement for that loop of copying A to B. So we're back here. That is the number of integers in that array. And we can run it. Looks not super great, but that's a clue. Num rows times num columns is the number of values in the array that we're copying. There are 50 values. And again, the nice thing about these pound defines, if I wanted to change this code to instead be 100 values, that's if I wrote this correctly, that's literally the only thing I changed, right? And the program still works. Now it's a 10 by 10 array. Let's keep it with 5 by 10 because that's what we started it with. It didn't copy them all. Looks like it copied a few, and then we got some random stuff in memory, right? It was just some junk-looking stuff in memory. Memcopy, and it's in the documentation, but you know it doesn't do it in like blinking bold font or anything like that. Count is the number of bytes to copy. There are num rows times num columns integers to copy, and how big is each integer? Yeah, it's a certain number of bits, a certain number of bytes. There's an operator in C that returns the number of bytes something is. It's been a while. Size of. And it would be size of int. Each of those elements is an int. And it's probably going to return 4 for size of, but it actually does depend on the system this is running on. It's not guaranteed to be 4. The C spec is annoying for that reason. But this function, and there's a bunch of functions we'll see operate on a number of bytes at a time. When we do dynamic memory allocation, it's going to be the same way. I want to allocate 126 bytes. You specify the number of bytes you're dealing with in memory, not the number of ints or number of floats. I want to copy that many bytes from A to B. I actually, can determine exactly how many bytes that's going to be at runtime. It's num rows times num columns, 5 times 10, times size of int. Each element is that many bytes. That's 4 for this system. It's going to copy 200 bytes. That will work when we run it here. It does. I mean, you could hard code that, but that kind of defeats the purpose of the rest, right? Okay, it's 200 bytes. That would also work, but that defeats the purpose of, having this program that's kind of somewhat flexible in terms of the number of things it can support via those kind of pound-defined macros, and then it's a little bit more portable as well. I could have just written 4 here, but that would only work on the systems for which size of int is actually equal to 4. Questions about this example? So the trade-off is there, I think. In your program, and all the time in the programs you'll be writing, you're going to want to copy one array from one to another. We'll look at an example of the actual source code for a memcopy-like function on Friday, if I remember to get to it. I think for now, suffice it to say, memcopy is going to be more efficient than your code. It's going to be better written. It's been looked at by hundreds or thousands of people over a period of decades now. It's going to be really highly optimized for your target computer. It's going to be a better thing in terms of performance. But I don't think the trade-off is that obvious otherwise. I mean, performance isn't always our primary goal. It can be. It isn't always our primary goal. Arguably, this code is a little bit easier to read. Arguably. This is also readable, but this requires you understanding how the memcopy function works, understanding that it takes the number of bytes, and understanding exactly what that is doing underneath the hood, what's just kind of encapsulated in this single function call in the standard C library called memcopy. So it's not as if one is strictly better than the other. You could argue that this is like the standard way when you want to copy one array to another. But you have to be aware of the sizes of the array and the size of each element inside the array, and then that function's, it's fewer lines of code, it's going to be higher performant. It's probably the better choice, but there's a little bit more maybe cognitive overhead of remembering what memcopy does, remembering that it's destination first and source second so you don't do it backwards, and remembering that you have to keep track of the number of bytes associated with it. I want to get to one more example, but we won't finish it today. We'll just get started with it. We had this code back a couple topics back of sorting 5 numbers. Let me bring up that code. And I mentioned that, by the end, once we learn a couple of other things, this code's going to be a lot cleaner, easier, maybe more scalable as well. This is from back in lecture 3. This is the sort values code that take as an input 5 integer values in any order, and its output was a printout of those 5 values sorted in ascending order. And we were playing around with the bubble sort algorithm. I might have to refresh this for this to work, but it's a little very streamlined sorting algorithm that looks at adjacent values in the array and checks if the bigger one is in front of the smaller one. And if so, it just does a local swap. So we look at 5, 1, we recognize that 5 is greater than 1, we swap. We then move on to the next one. 6, 7 is fine. We move on to now 7 and 2. 7 is greater than 2. We do that swap, and then we continue to do so until there's no longer any swaps remaining. The end result is an array that is sorted in that, or a set of values that are sorted in that order. We wrote the code for this, and even at the time we recognized it was a little bit ugly, right? We did comparisons. We had just 5 scalar values because we hadn't learned arrays yet. So we'd have to do some refactoring if we wanted this to work with 6 values or 7 values or 8 values. And we just kind of did our if statements. We just checked v1 greater than v2, swap them. Then we looked at v2, 3, 3, 4, and 4, 5. And at that point, we had one value that was guaranteed to be the right position. And then if you recall what we did at this point, we just kind of copy paste that whole block of code 4 more times to kind of get the same result of the whole thing sorted at the end. And it worked for 5 values. Worked pretty nicely for those 5 values that we had here. But if we wanted to make this now 6 values, that would be very annoying. Doable, but kind of annoying, right, to refactor our code. If we wanted to do this for 6 million values using this code, probably not possible. The likelihood of you making a mistake along the way is pretty high. If it was going to be for 6 million values, that'd be a very long piece of source code. It probably wouldn't even compile properly. Now with our understanding of arrays, we can take this exact same logic, which is just comparing 2 nearby elements to each other and swapping if v1 is greater than v2, if the element at this location is greater than the element next to that location, and get a sorting code using for loops instead of just all this copy-pasting code here that should be able to sort an arbitrary number of elements within reason here using fewer lines of code than what this example itself it had already back for lecture 3. But we can't get to that right now because class is over. So on Friday, come on back and let's sort some values. And then we're going to start to mess around with strings, and I think we'll have a little fun on Friday.